Let's imagine, just for a moment, that we have a spaceship. And no, I don't mean some magical science fiction ride like the Millennium Falcon. I'm talking about an actual, real spaceship, the kind that could genuinely be built in our lifetime, using technology we already understand today. Nothing fantastical, just solid engineering. Now, here's the catch. That means we can't go zipping off to visit every star twinkling in the night sky. But it does mean something pretty exciting. We could visit every single planet in our own solar system. Think of it like a cosmic bucket list, a grand tour of planetary destinations. So the big question becomes, how long would it actually take to check off every single one? Well, buckle up, because the answer is way more complicated than you'd expect. To navigate through space, we have to go head-to-head with some of the most fundamental forces in the universe. And we have to push our humble little spacecraft right up to the edge of what's physically possible. Just like any great road trip, the very first thing we need is a map. But here's the twist. Our map of the solar system isn't like any map you've ever used before. The biggest difference is that you simply cannot measure the distance between 2 points and call it a day. Why? Because of motion. Everything in the solar system is in constant motion, orbiting the sun in a never-ending dance. That means there are no straight lines out there, only curves. Right now, as you're listening to this, planet Earth is racing around the sun at a jaw-dropping 107,000 kilometers per hour. Meanwhile, every other planet is doing its own thing too, moving along its own unique orbital path at its own particular speed. So when we launch a spacecraft toward, say, Jupiter, we're not aiming for where Jupiter currently sits in the sky. We're aiming for where Jupiter is going to be by the time our spacecraft actually arrives there. It's kind of like throwing a dart at a moving target, except you're doing it from the back seat of a moving car. And to make things even trickier, in space you only get one shot at hitting that target. There's no do-over. If you miss, you just kissed goodbye to an entire decade of planning and a few $100 million, all vanish down the drain in an instant. So why is there absolutely zero room for error? It all comes down to fuel, arguably the most precious resource you can have out in space. Picture this. You're driving toward a destination, and your car's gas tank has been filled with the exact precise amount of fuel needed to get there, assuming you drive in the most efficient way imaginable. Now, if you take even one wrong turn, you're stranded. Even something as simple as speeding up too much or slowing down too often means you'll run dry before you ever reach your destination. Stressful, right? Well, that is essentially what every single journey through the solar system looks like. So, in order to squeeze every last drop of value out of our limited fuel supply, we need to team up with the single most powerful force in the entire universe: gravity. But here's the irony. Before we can work with gravity as our ally, we first have to fight against it as our enemy. To even reach space in the first place, we need to break completely free of Earth's gravitational grip. Now, this isn't necessarily the hardest leg of the journey, but it is by far the most energy-hungry. Our rocket burns through enough fuel to fill an entire Olympic-sized swimming pool every single second. For the full 2-minute burn it takes just to climb above Earth's atmosphere and cross that invisible threshold into outer space. Once we're there, we're officially orbiting Earth, cruising along at just over 20,000 kilometers per hour, faster than Earth's own rotational speed. That extra burst of velocity lets us effectively outrun the pull of Earth's gravity, allowing us to travel in a circular path around the planet. Now here's where things start to get delightfully strange. Consider this your crash course introduction to orbital mechanics. From our point of view aboard the ship, we feel like we're traveling in a perfectly straight line. Our spacecraft isn't steering itself around Earth like a race car looping around a track. Instead, it's Earth's gravity that bends the very fabric of space itself, shaping our path into a graceful curve. Here's the key insight. The harder we push against gravity with our engines, meaning the faster we go and the more fuel we burn, the straighter that curve becomes, and the farther from the planet we're able to travel. But flip that around, and if we slow down instead, gravity bends our path even more sharply. And if that curve bends too much, we end up on a direct collision course with Earth's surface. Definitely not something we want to experience firsthand. So by doubling our velocity to over 40,000 kilometers per hour, again faster than Earth itself, we finally managed to break completely free of Earth's gravity and officially begin our journey between the planets. At this point, our total speed relative to the Sun clocks in at around 150,000 kilometers per hour. Now we've become just another object hurtling through the solar system, alongside everything else out there. But don't get too comfortable, because we still face some serious limitations. Just like every planet, moon, asteroid, and comet in the neighborhood, we're now captured by the gravitational pull of the Sun. It's essentially the same situation as orbiting Earth, just scaled up to an enormous degree. Since most of the solar system exists roughly along one flat plane, that means there are really only two directions available to us, either toward the Sun or away from it. But no matter which direction we choose, our path is always going to curve around that massive gravity well. Remember, no straight lines allowed out here. And just like when we were orbiting Earth, we control our trajectory by speeding up or slowing down. Sounds simple enough in theory, right? If our only goal was to wander aimlessly through the solar system, this would honestly be pretty easy. But if we actually want to steer our spacecraft toward a specific destination and then successfully settle into orbit once we arrive, that requires some seriously precise calculations. Anyway, there's really no better way to figure all this out than by just diving in and giving it a shot. So let's set our course for the very first planet from the Sun, Mercury. Now, you might be surprised to learn that Mercury is actually the single hardest planet in our solar system to reach. And honestly, that makes it the perfect choice for our very first mission. Because if we can crack the code on how to get there, everything we learn along the way will set us up perfectly to tackle the rest of the solar system with relative ease. In terms of raw distance, Mercury is actually pretty close to Earth, only about 80 million kilometers away. But it sits even closer to the Sun, orbiting at an average distance of just 58 million kilometers. And because Mercury is tucked so deep inside the Sun's gravity well, it has to move incredibly fast just to avoid getting swallowed up. We're talking about a planet zipping along at roughly 170,000 kilometers per hour. Given our current velocity, we're now facing two major challenges that need solving. First, we need to slow down enough to actually begin falling toward the Sun. And second, we need to carefully control that fall so that we arrive safely into orbit around Mercury without accidentally overshooting and sailing right past it. So starting from our current position, just beyond Earth's orbit, we need to slow down significantly, cutting our velocity down by almost half. Essentially, we're undoing pretty much all the hard-won speed we gained just to escape Earth's gravity in the first place. In doing so, we're deliberately losing the tug-of-war against the Sun's gravity, allowing it to gradually curve our flight path downward until it begins to intersect with Mercury's orbit. And here's the thing, that part is actually the easy half of the equation. Sure, it means burning through yet another chunk of our precious, limited fuel supply. But it also sets the stage for an even bigger, trickier problem that we're going to have to solve next. So let's think about falling into the gravity of the Sun. It's kind of like rolling down a hill. At first you tumble slowly, but the further you fall, the faster you go. That's just how gravity works around the Sun. The closer you get to it, the harder it pulls on you. So even though our spacecraft has to slow down at the very beginning of the trip, we're actually going to end up moving a lot faster as we get closer to our star. In theory, that speed boost should help us catch up to Mercury. But here's the real challenge. We're going to end up going way too fast by the time we get down that far into the solar system. Our fall down this gravitational hill will accelerate the ship to somewhere around 210,000 kilometers per hour. And that's exactly where our problem kicks in. The ship needs to slow down for a second time, or we'll just blow straight past Mercury without ever catching it. This is actually pretty close to what happened to an old NASA mission called Mariner 10. It launched back in 1973, and it used this exact falling down the hill method to reach Mercury in just about 5 months. Sounds great, right? Well, the downside was that by arriving so fast, the probe was completely unable to slow down enough to settle into orbit around the planet. So instead of orbiting Mercury, it ended up gathering as much data as it possibly could while flying straight past it in a single flyby. Now, in theory, we could just burn our engines again to bleed off all that extra velocity. But doing that would blow through our fuel supply so badly that it goes beyond anything realistically possible for a spacecraft to carry. And that's exactly why Mariner 10 ended up with the fate it did. In reality, there has been only one NASA mission that successfully made it all the way into orbit around Mercury, the Messenger probe, launched in 2004. And here's the kicker. It took 6.5 years to complete the trip from Earth. Why so long? Because that probe used the gravity of Earth, Venus, and Mercury itself to achieve the same slowing effect that would otherwise require an impossible amount of fuel. The trade-off is that this method requires multiple loops around the Sun to line up all those planetary encounters just right, which is why the journey stretched out over so many years. So, following the same path that the Messenger probe carved out, our first target on the way to Mercury is actually going to be the planet Venus. The idea is that we're falling toward the Sun in such a way that our path takes us right past Venus. And the goal is to get close enough to that planet that its own gravity starts to bend the direction of our spacecraft. We call this maneuver a gravity assist because we're essentially letting a planet's gravity help us steer. And here's why that matters. If gravity is doing the work of changing our direction, our engines don't have to work as hard, which means we save precious fuel. In this case, we'll approach Venus in a way that its gravity pulls our flight path upward just a little. So we're still falling toward the Sun, but now the hill isn't quite as steep as before. This sets us up to swing all the way around the Sun and catch up with Venus again for a second gravity assist. Only this time, we come in much closer to the planet, within just a few hundred kilometers of its surface. That closer pass lets gravity bend our trajectory even more sharply. And this change in direction is exactly what sets us up for our first encounter with Mercury. The Messenger probe, which our flight plan is based on, actually had to fly past Mercury 3 separate times over the course of nearly 2 years. Each time, Mercury's gravity nudges the spacecraft's path just a little bit further, gradually bringing it closer and closer to matching the planet's own orbit. After that third gravity assist from Mercury, the spacecraft is finally close enough to make one last course correction and slip into a stable orbit around the planet. At this point, we'll need to fire up the main engines again for the first time since we began our long plummet toward the Sun. We'll time this burn precisely so it slows us down right as we pass close to Mercury. Now, Mercury is a small planet with fairly weak gravity, only about a third as strong as Earth's. But if we manage to slow down just enough at exactly the right moment, Mercury's gravity will actually be able to outpull the Sun's gravity on our ship. That's what finally curves our path into a stable orbit around the planet. All of this assumes we've got a bigger, more powerful ship than the old Messenger probe, but we'll still need to perform a similar series of gravity assists to lock in our final trajectory, looping around the Sun multiple times before we finally arrive. All told, the journey from Earth to Mercury is going to take us about 5 years to complete. Now here's some good news. Not every interplanetary trip has to be this complicated. Take Venus, for example, our closest planetary neighbor and also our shortest trip through the solar system. But don't mistake short for boring. Starting from just beyond Earth's gravity, we know we need to head down toward the Sun, which means firing up our main engine to shed some orbital momentum and begin falling down that gravitational hill. That gets us to Venus pretty quickly, in about 4 months. The Sun's gravity pulls us down to line up with Venus's orbit. But just like with Mercury, we're now moving way too fast to simply get captured by Venus's gravity. Without slowing down, we just sail right on by. Fortunately, this time we've got more tools at our disposal. First, Venus is a much bigger planet than Mercury, so its gravity has almost 3 times more pulling power to bend our path and lock us into orbit. Second, Venus actually has an atmosphere, and a seriously thick one, almost 100 times denser than Earth's. So by flying in close and skimming the upper edge of that atmosphere, we can slow ourselves down significantly just through aerodynamic drag, kind of like a skydiver using a parachute to cut their speed. Combine that atmospheric braking with the planet's gravity and one solid burn from our main engine, and we can settle our spacecraft into orbit around Venus in under 5 months from our departure from Earth. Now, when it comes to reaching our next destination, Mars, everything flips completely. This time, we have to fly away from the sun instead of toward it for the very first time in this journey. That means the whole game becomes about acceleration, climbing up the hill of the sun's gravity instead of falling down it. And here's the twist. Slowing down when we get there is actually going to be even harder than before. Now, spacecraft from Earth have made the trip to Mars many times over the past 4 decades. It's by far our most visited planetary neighbor in the solar system. Because of that experience, we've developed a method for getting there that prioritizes fuel efficiency over raw speed. It's called the Hohmann Transfer Orbit. The strategy is simple in concept. We wait until Mars and Earth line up just right in their orbits around the sun, at their closest approach to one another, an alignment that happens like clockwork, giving us the most efficient possible path between the two worlds. That alignment only comes around once every 2 years, but during that window, all we really need to do is launch our spacecraft from Earth and speed it up just a little bit faster than our own planet is already moving. That small boost is enough to send us climbing outward, away from the sun's gravity well. Now, in theory, we could crank up the throttle even more and reach Mars in record time, but that would only create a bigger headache once we actually got there. Here's why. Mars orbits farther from the sun than Earth does, which means it travels at a noticeably slower pace. So if we're accelerating away from Earth, we're eventually going to have to shed a huge amount of that speed by the time we arrive at Mars, dropping from around 150,000 kilometers per hour down to about 86,000. And unlike our trip to Mercury, there's no convenient planet along the way to give us a gravity assist. And unlike Venus, Mars doesn't have a thick atmosphere we can use to brake against. On top of that, Mars has a much weaker gravitational pull than Earth, so the entire burden of slowing down falls on our spacecraft's engines and the fuel we're burning. That's exactly why the trip to Mars takes roughly 8 months. We could technically get there faster, but we'd blow right past it, unable to slow down enough to settle into orbit. Now things get really interesting once we set our sights on Jupiter, because this is where we finally venture deep into the outer solar system for the first time. Jupiter sits about 5 times farther from the sun than Earth does, so we're looking at another long haul. That kind of distance means we can't just casually hop from one orbit to the next the way we did on the trip to Mars. Instead, we go back to the gravity assist trick we used on our way to Mercury. Back then, we used Venus's gravity to bend our path downward, toward the sun. This time, we flip the technique around. We can use a planet's gravity to fling us outward instead, sending us on a direct trajectory toward Jupiter. Once we're underway, there are 2 big challenges waiting for us. The first is crossing the asteroid belt, that vast stretch of space between Mars and Jupiter packed with hundreds of thousands of rocky objects, everything from tiny specks of dust to asteroids the size of small moons. At the speeds we're traveling, even a collision with a tiny rock could be catastrophic. If this were a science fiction movie, that would be a real nail-biter of a scene. But in reality, space out there is mostly empty. The rocks are spaced so far apart that you could fly through the entire belt 100 times over and statistically never come close to hitting one. Basically, all those dramatic asteroid dodging scenes in movies are pure fiction. The belt is far more empty than crowded. So once we make it through the asteroid belt, we run into challenge number 2, and that's Jupiter itself. This planet is an absolute giant. It's 2.5 times more massive than every other planet in the solar system combined. Just picture that for a second. Take Saturn, Uranus, Neptune, Mars, Venus, Mercury, and Earth, stack them all together, and Jupiter still outweighs the whole pile by a factor of 2.5. Naturally, that means the gravity around Jupiter is incredibly powerful, almost like it's a smaller version of the Sun. So just like the Sun did earlier in our journey, Jupiter's gravity starts reeling us in as we get closer. In a sense, we go from climbing up the hill of the Sun's gravity to falling down the hill of Jupiter's gravity instead. That's great news for building up speed and getting where we're going faster, but it brings back our old nemesis, the problem of slowing down. Out here in the depths of space, far from the Sun's intense gravitational grip, everything moves at a much more leisurely pace. Remember how Mercury was zipping around at roughly 170,000 kilometers per hour? Well, Jupiter cruises along at a much calmer 47,000 kilometers per hour. Meanwhile, our spacecraft is barreling along at over 5 times that speed. So clearly, we've got some serious deceleration ahead of us. Jupiter's gravity is honestly both a blessing and a curse here. On one hand, it pulls us in and accelerates us even further. But because that gravitational force is so overwhelmingly strong, it's actually capable of bending our flight path into a stable orbit, even while we're still moving faster than the planet itself travels. This means we don't need to slow all the way down to match Jupiter's leisurely orbital speed. We just need to shed enough velocity to get captured by its deep gravity well. For a real-world comparison, when the National Aeronautics and Space Administration's Juno spacecraft approached Jupiter back in 2016, following a path very similar to the one we're describing, the probe had to fire its main engine continuously for 35 minutes straight, just to lose enough speed to be captured into orbit. So let's take stock of everything that's happened so far. We fell toward the Sun, gained speed, looped around Venus, got flung outward into deep space, crossed the asteroid belt, fell into Jupiter's gravity well, and then slowed back down. All of that has taken roughly 3 years to accomplish. Now here's a genuinely fun question to consider. What happens if we don't slow down at Jupiter? Well, the answer to that is actually the key to unlocking the rest of the solar system. To reach Saturn, we essentially repeat the whole process, but this time, we use Jupiter's own gravity as our slingshot. If we hold on to our velocity instead of shedding it, we'll be moving too fast for Jupiter to fully capture us into orbit. But its gravity is still plenty strong enough to bend our trajectory as we zoom past. Think of it like falling down one hill, curving around a sharp right-hand turn, and then climbing back up another hill on the other side. All that extra speed we picked up on our approach to Jupiter, we end up losing again as we fly away from it. In a way, the two hills cancel each other out, but here's the payoff. The curve in our path now points us directly towards Saturn. At this stage, our biggest obstacle isn't gravity or speed, it's sheer distance. If you look at a typical diagram of the solar system, Jupiter and Saturn might look like close neighbors, but that's purely an artistic choice, made so the whole system fits neatly on one page. In reality, Saturn sits almost twice as far from the Sun as Jupiter does. So we end up spending several years simply coasting through empty space between these two gas giants. Eventually, though, the iconic rings of Saturn start to come into view. Now, even though Saturn is enormous, roughly comparable in size to Jupiter, it's actually much less massive, weighing in at only about 1/3 of Jupiter's mass. That also means its gravitational pull is only about 1/3 as strong, so we don't need nearly as much thrust from our engines to counteract it. That makes slowing down and settling into orbit around Saturn a comparatively easy maneuver. All that extra coasting time, though, stretches our total journey from Earth to Saturn out to nearly 7 years. And now, it's time to set our sights even further out, toward Uranus. By this point in the journey, you can probably guess what comes next. We repeat our gravity-hopping strategy, using the inner planets to build speed, and then leaning on Jupiter as our major springboard into deep space. This time, we can also add Saturn to our toolkit, using its gravity to curve our path even further outward, toward the edges of the solar system. But there's an important catch to keep in mind here. In order to chain multiple gravity assists together like this, using one planet after another in sequence, all of those planets need to be lined up in very specific positions at the moment we launch from Earth. They have to be arranged just right, so our spacecraft can swing from one gravitational slingshot to the next in a smooth, continuous chain, rather than missing its window and drifting off course entirely. Unfortunately, that kind of perfect alignment doesn't happen very often at all. Back in the year 1977, the Voyager probes took full advantage of a rare planetary lineup that made what's called the Grand Tour of the solar system possible. Every outer planet lined up just right, letting those spacecraft hop from world to world using gravity like a slingshot. But here's the catch. That exact same alignment won't happen again until the year 2152. And honestly, by that point, we'll probably have some kind of warp drive that can zip you anywhere in an instant, so the whole alignment thing won't even matter anymore. But don't lose hope for reaching Uranus in our own lifetimes. There's actually a launch window opening up in the year 2031 that would let a spacecraft use gravity assists around both Venus and Earth to slingshot itself onto a path toward Uranus, arriving in about 13 years. And honestly, that's not bad at all, when you consider that Voyager 2 took roughly 9 years to get there, and it was using one of the rarest planetary alignments in history to do it. Now let's talk about Neptune, the farthest official planet from the Sun. At least, that's what they want you to believe. The distance involved here is almost impossible for the human brain to really grasp. Neptune sits about 30 times farther from the Sun than Earth does. That's 6 times farther out than Jupiter. Out at that distance, sunlight is so weak it barely even registers as light anymore. After swinging past Uranus and grabbing a gravity boost, the Voyager probe needed another 3 years of coasting through empty space just to reach Neptune, bringing the total flight time to about 12 years. Keep in mind, those old Voyager probes didn't have powerful engines strapped to them. They relied almost entirely on gravity to steer and accelerate them through the void. So over a distance that massive, a modern spacecraft with real propulsion could probably start closing the gap, even without a perfect planetary alignment to help it along. That would bring our estimated travel time down to around 15 years at the most. Now, technically speaking, Pluto isn't classified as a planet anymore. It really depends on who you ask, and that debate still gets people fired up. But let's go there anyway, because it's fascinating and because there's already been one successful mission from the National Aeronautics and Space Administration to reach it. That mission was called New Horizons. The only real problem was that by the time this probe finally reached the very edge of the solar system, it simply didn't have anywhere near enough fuel left to slow itself down and settle into orbit around such a small, slow-moving object. To put it in perspective, Pluto travels around the Sun at only about 17,000 kilometers per hour, while New Horizons was screaming past at roughly 83,000 kilometers per hour by the time it reached Pluto's orbit. Because of that incredible speed difference, the probe was able to make the entire journey from Earth to Pluto in just about 10 years. But if we actually wanted to slow down, settle in, and orbit Pluto the way we did with the other planets, settle in, that would realistically take closer to 20 years to pull off. Let's step back for a second. We've now virtually visited 8 planets, plus 1 dwarf planet for good measure. How long would all of that actually take? Well, if you add up every single leg of the journey, we've clocked in at just over 64 years of total travel time to reach every destination in the solar system. That's the kind of massive undertaking you'd probably want to begin as a kid. Or at the very least, pick your favorite destination strategically and focus on that one. But if you're looking to start learning about every planet in real detail, there's honestly no better place to begin than Mercury. You'll want to see the shocking discovery that the National Aeronautics and Space Administration made there, and you can catch all of that in the video appearing on your screen right now.